So I have already told you about the metamorphism, about the Pelitic rocks. What are the Pelitic rocks? Okay, Pelitic rocks are basically fine-grained rocks. Okay, containing phyllosilicates in a major proportion. Apart from that, they contain quartz in a 10 to 30% proportion. Greater than 50% is phyllosilicates. Phyllosilicates like they contain clay and mica minerals. Okay, clay and mica minerals like chlorite. Okay, chlorite, your lomonite. Okay, montmorillonite, kaolinite. These minerals are there in pelitic sediments. After pelitic sediments undergo metamorphism, they are called as metapelites. Okay, you have studied about the basic rocks and the carbonate rocks. In the basic rocks, the general zone, the zone like means the phases. Okay, you know the names of the phases: brainite, pumpelite, green schist, amphibolite, granulite, blue schist, eclogite. Like that, in case of carbonaceous rocks, okay, carbonaceous rocks. You have studied the zones: talc zone, tremolite zone, diopside zone, fosterite zone. Okay, like in silicates, you have studied ankerite zone, geosite zone, biotite zone, amphibole zone. Okay, like in case of these phyllosilicates, rich and quartz rich rocks, these are called as pelites. These pelites have also a particular sequence of growth. Okay, with change in temperature and pressure, they also change to particular mineralogy, or we can say a particular mineral appears at certain pressure and temperature condition. This appearance of certain pressure and temperature condition is first studied by Barrow. Okay, first studied by Barrow where in Barrow, first studied by Barrow in Scottish Highland. Okay, Scottish Highland. There is a place. This is called as Scottish Highland in Scotland only. Okay, and he found out that these minerals, CbGSKs, chloride biotite garnet, chloride sillimanite, CbGSKs. Okay, these minerals are formed or are like appear at particular temperature pressure conditions. So we can define these minerals. We can take these minerals as the characteristic of that grade of metamorphism. Okay, so when experiments were conducted regarding the metamorphism of pellets. This sequence is found, and they have noted down the reactions and how the change occurs. We will study about that. About these pellets, or we can say cells, mud rocks, okay, mud rocks, clay stones, okay, clay stones. These all come under pelites only. Okay, all the fine grained rock comes under pelites only. They can be defined by this Kf mass system. Okay, K2O, FeO, MgO, Al2O3, SiO2, H2O. These six components can define all the pelites. Okay, can define all the pelites. So this was also a question in previous year GSI, that which of the following composition best represents the cell rock. Okay, so the answer is that Kf mass system. Okay, Kf mass was there, like K2O, FeO, MgO, Al2O3, SiO2, and H2O was there. The option was there. So um, so all the fine grained rocks can be defined by this composition. Okay, so we just in the growth of this CPGSKS, we represent them in a AFM diagram. So you have studied about the AFM diagrams or not? So we'll first continue that diagenesis and low grade metamorphism of pelites before they go into a they develop some zones like this cross-CPG SKS, they first undergo diagenesis. After the deposition of the sediments, they all undergo diagenesis. Okay, so during the diagenesis, these many of the alterations occur. These alterations are noted here. You can just go through these things. Okay, the originally clay is gradually replaced by more thermally stable clay elite. Okay, these are simple sentences that what kind of alterations occur there. Okay, you can go through these things that these things occur in the diagenesis condition. Okay, but the main thing is this elite crystallinity. Okay, this elite crystallinity is elite crystallinity acts like a geothermometer. Geothermometer. What about this geothermometer? See, there are two things: geothermometer and geobarometer. Okay, two things. In compositing the two things, we make a study. This is called a geothermobarometry. Okay, geothermobarometry. So geothermobarometry can be done by the two things. Also, I am completing this thing. Okay, so give attention. Okay, geothermobarometry is also a chapter subject in metamorphism. Okay, so I am just giving introduction. Next time when I will teach you in geothermobarometry, I will just show you the reactions. So geothermobarometry is like it consists of two systems. One is geothermometer, another is geobarometer. Okay, now just what is this geothermometer? This thermometer. So basically these are reactions. Okay, basically these are reactions. These are reactions that occur at particular temperature and pressure. Okay, the temperature and pressures for these reactions are defined. Okay, are defined. पूरा fixed है, are fixed. You can say also fixed. So when these reactions occur, na, we can say these temperature and pressure are like this. Okay, now what is the difference between this geothermometer and geobarometer? So geothermometer is a reaction where the reaction is independent of independent of pressure change. Okay, or independent of change in pressure. So geothermometer is a reaction which is independent of change in pressure. That means it is highly dependent in dependent of the change in temperature. Okay, highly dependent geothermometer. Geothermometer. It is highly dependent on the change of pressure. Okay, pressure. Sorry. Temperature. Temperature. Okay. Or you can say it is highly sensitive to change in temperature. Highly sensitive. Okay, sensitive to change in temperature. Okay, highly sensitive to change in temperature. So what will happen in this thing? Like these reactions will change at particular temperature. Okay, these reactions will not occur at like variable temperature. Okay, these reactions uh, change their change their way of reacting when temperature changes. Okay, temperature changes. So these are called a geothermometer. Okay, geothermometer. Now geobarometry, geobarometer. Okay, Now geobarometer. So geobarometer are similar to this geothermometer, but these are highly sensitive to pressure change. Okay, or change in pressure, but a little or not sensitive to change in temperature. Okay, change in temperature. Now we can get that where this pressure was this quantity, the quantity of the magnitude of the pressure will get where this particular geobarometry reaction occurred. Okay, if the geobarometric reaction occurred at some place, or we will see na this how we will know, that this reaction occurred, because we cannot know simply, means we cannot see in our naked eye, na, because we always see the product side, na, we always see the product, not the reactant. In nature, in metamorphism, I am saying, okay, we cannot see the reactant because we don't know na what was the earlier things were present. We only know the products. Only can see the products. Okay, how we know this? These are like replacement. Like kyanite is replaced by silimanite. Okay, kyanite is replaced by silimanite. So what this uh, texture will infer? What can we infer from this texture? That if kyanite is replaced by sillimanite, then there was a high pressure condition, but gradually it changed to the high temperature condition. No, because kyanite is a high pressure mineral, sillimanite is a high temperature mineral. So if kyanite is replaced by sillimanite, so the conditions have changed from high pressure to high temperature. Okay, these textural studies only indicates this geothermometer, geobarometer. So basically, this geothermometer and geomatometers are nothing but textures only. Okay, textures only. Indirectly, these are textures only. Indirectly, from that textures, we study the reactions. We infer the reactions from this replacement type of thing. Okay, like growth zoning of garnet. This is also there. Growth zoning of garnet. Growth zoning of garnet is a world class, like high class geothermobarometer. Okay, growth zoning of garnet, it denotes both temperature and pressure, and precisely. Okay, so what happens in growth zoning of garnet? The basically the manganese bearing garnet. Okay, these are very important because they are very sensitive to pressure and temperature. But other garnets can also be used. Okay, other garnets can also be used, but manganese bearing garnets are very much sensitive. Okay, than other garnets. So these garnets when grow, consider this is manganese rich core, manganese rich, Mn rich core. Then when this garnet grows, the temperature and pressure changes because the garnet is crystallizing na, so temperature is declining. Temperature is declining, that's why garnet is crystallizing na. So when this garnet grows, this outward composition changes slowly. Okay, this outward composition changes slowly, dependent on the temperature and pressure, both temperature and pressure. Okay, so each of this ream can denote a temperature and pressure condition. T1 P1, T2 P2, okay, T3 P3, T4 P4, T5 P5. Okay, each of these zone can represent a uh, particular temperature and pressure condition. That's why this garnet growth zoning is a very very much sensitive geothermoparametric indicator. Okay, everyone understood what is geothermobarometry or what is a geothermometer or what is a geobarometer? Pellitic. Okay, so now this elite crystallinity is a good geothermometer. That means temperature is increasing like this elite crystallinity also increases. Okay, like in vitrinite reflectance. Okay, vitrinite reflectance. This vitrinite reflectance suggests the degree or the rank of qualification. Okay, you have known these macerals, vitrinite, exenite, humanite. Three type of macerals are there: vitrinite, exenite, humanite. Okay, apart from that, there are lithotypes and microlithotypes. In coal, okay, in coal, three types of macerals are there: vitrinite, humanite, exenite. Okay, maybe some terminology. Vitrinite, liptinite, exenite. Yes, vitrinite is also known as humanite. Vitrinite, also known as humanite. Okay, humanite. I think. Okay, don't I'll tell you when I'll go to coal. Okay, when I'll teach you coal, then I'll tell you in detail. Vitrinite, liptinite, exenite. Okay, there are three types of macerals are there in coal. These are basic building blocks of coal. Okay, from these you can these the lithotypes and microlithotypes are made. Lithotypes and microlithotypes. Lithotypes are bittern, clarent, diurine, fusion. Microlithotypes are bitrate, claret, diurate, fusate. Okay, these are microlithotypes there. So this vitrinite is the highest rank. Okay, this vitrinite is the highest rank. Like this vitrinite is made from this vitrinite maceral. This vitrinite maceral is made from the humus material. Okay, humus material. So the vitrinite, when it undergoes qualification process, any humus material undergoes qualification process. This vitrinite reflectance means how much we have incidented on that light on that surface, how much you have incidented light on that surface, and how much it reflected. Okay, so that vitrinite reflectance shows the degree of qualification, that how high the rank is, how high the rank of the coal is. Okay, with a good vitrinite reflectance, the coal will be a very good coal. Okay, that is the thing. So in the institute, there is a coal sample. The layers are clearly distinguishable. Okay, there is a coal sample in institute. You can see those who are in institute. So the layers are clearly visible. So like that, elite crystallinity has a good like hold in this pellitic rocks, and it signifies that what amount of temperature, because it is a geobarometer, na? Geothermometer. Elite crystallinity is a geothermometer, so it will signify the temperature condition at what that pelite has formed. Okay, everyone got it? Okay, but and other things are only the what the changes occurs at diagenesis condition. That things are written only. You can go through it. Okay, you can go and have a read these things. Okay, so we'll go to the metamorphism of medium temperature pressure metamorphism of pelites. Medium PT metamorphism pelites, the classical Barovian sequence develops here. So these things are represented in a grid. Okay, this is called as KF mass grid. Okay, KF mass grid, PT grid, KF mass PT grid. Okay, in this thing, Here this is pressure, here this is temperature. Okay, with the variation of the pressure and temperature, don't be afraid. Okay, this diagram is only for representation. Only you just see this diagram for once and never see this for twice. Okay, इसको देखने का कोई जरूरत नहीं है दोबारा, कुछ प्रॉब्लम नहीं है इसको, ठीक है। इसको बस तुम जान जान लो कि भाई ऐसा एक डायग्राम है। ओके, एटलीस्ट ये जानना चाहिए कि ऐसा एक डायग्राम है, ठीक है। दिस इज केएफ मास पिट्टी ग्रिड। Okay, PT grade means this is pressure, this is temperature, and these all reactions are put here. Okay, like this is reaction 1, okay, this is reaction 2, okay, and you can trace here all the reactions those occur, reaction 3, 4, 5, 6, 7, 8, 9, 10. Okay. So these are all reactions that occur at particular pressure and temperature condition. Got it? So these reactions are traced here. Like I have, like I have taught you in the calcareous protolith. Like I have taught you in the calcareous protolith based on the temperature and XCO2, the partial pressure of carbon dioxide. Okay, or you can say the composition of carbon dioxide. Similarly, this is also a diagram based on temperature and pressure. Okay, nothing else, but this diagram is too much complicated, and you like I will make you understand this diagram, but it is not of any benefit for you. Okay, so ये बस टाइम वेस्ट करना होगा। ये डायग्राम कभी ये आता भी नहीं है, मतलब इसको करना नहीं होता। पेलिटिक रॉक ऑलवेज कम्स इन द एग्जाम। ओके, पेलिटिक रॉक ऑलवेज कम्स इन द एग्जाम। So carbonaceous rocks never come. Okay, always basic pellitic. These things come repeatedly. So okay. So first, the chloride zone develops from this after the diagenesis process. This chloride zone develops. Okay, after the diagenesis process, chloride zone develops. So in the chloride zone, basically, the cells convert to slates. Okay, you know that sequence, na? You know that sequence: cell, slate, phyllite, cyst, and niche. This is the increasing degree of metamorphism. Increasing degree of metamorphism. Okay, so this is the first chloride zone. In chloride zone that develops at 350 to 450 degrees Celsius. Okay, this is the AFM diagram. In the AFM diagram, I have told you that day how they represent actually. In the AFM diagram, this is the projection from a cave diagram only. Okay, this is the a cave diagram. Okay, they project this to AFM diagram. Means you can say this is A K F M. Sorry, A K F M. Okay, so here you can plot. You know the AKF diagram. Okay, you know the AKF diagram. So you can plot like chloride here. Okay, you can plot chloride here. So you have to. This is Moscovite. Huh? This is Moscovite. Potassium and aluminium. Okay, Moscovite. So what we do? Okay, what we do? We project everything from this Moscovite. Okay, project everything means this chloride zone, like the chloride compositional zone, will be projected from this Moscovite. So this will be projected towards this. Okay, and this will be the chloride. Okay, this will be the chloride. Okay, now you see this diagram from this side. So this diagram will look like this. This is chloride. Okay. So I gave basic introduction because it was needed for this thing. Okay, like you can see a cave diagram here. If there is three component x, y, z, and this diagram changes, a cave diagram. This diagram changes to this. Okay, so it is z or there is z, x. Okay, now you can write. This line is not there. This line is also not there. So you can write this x plus y plus z gives x plus z plus A. Okay, A means that any mineral should be there. Okay, you can write like this, or you can just write y plus z gives z plus A. No, no, no. Z is common, na? Z is common here. Z is common here. Z point is not changed. Okay, so you can write y plus x. Y plus x give z plus A. Okay, this can this you can write. Okay, like this only a cave diagrams, a FM diagrams all work. Okay, so 350 to 450 degrees Celsius chloride appears after the diagenesis process. Okay, so here in a FM diagram chloride is represented. Don't go to this diagram because we have to go to the previous diagram. These diagrams are actually not important. When writing the long question, you can avoid these diagrams. Okay, Z plus A and X plus A. Oh, you will see that in your SAP diagram class. Okay, like this is your x plus y plus x, z plus a, x plus a. X plus a, it will not x plus a. Okay, it will be z plus a. X. These lines we do not consider these lines. We only consider these in between lines. Okay, so বুঝিপারল শ্রীপতি? So these lines, these diagrams actually not much of importance. If you will draw this diagram, then some extra impression marks you will get. Okay, nothing else. Okay, like 1 or 2 marks you will get. But it's better to draw the diagram after understanding these diagrams. It will like if you will draw these diagrams, it will not only increase your marks in the same question, also that same impression remains for the whole copy. Okay, that is the benefit of writing a good and neat and clean with all details long question. If you are writing a very good long question from the starting, it will make an impact on the examiner's head that yes, this student knows many. Okay, this will strike his head. The student knows things. So after you will like make a this uh, this long question, a good long question, there will be a good impact. Okay, that will impact your whole copy. Otherwise, not much of importance. Okay, so chloride developed. Okay, these things you will just go through. There is not much of good things. Okay, chloride developed. After the chloride development, what will happen? Biotite will develop. Okay, so biotite zone. So chloride, what happens? This chloride reacts with potash feldspar and gives biotite. Okay, one biotite isograt reaction that can affect pelite is encountered at point 2 in Kf mass grid. Okay, you can exclude this Kf mass grid. I have told you. Okay, in which chloride reacts with potash feldspar to produce biotite and phengite rich mica. Okay, this muscovite, phengite rich muscovite. Chloride reacts with potash feldspar. This reaction you have to remember. You have to memorize simply. So chloride reacts with potash feldspar and gives biotite plus muscovite. Okay, here you can see this chloride. Okay, this chloride reacted with potash feldspar. Okay, potash feldspar is not here. Okay, here in the above part it is aluminium. These things come in between. Na? I cannot see the things. Okay, in my whiteboard there are so much options in the thing. Na? They are overriding on my PPT, so I cannot see the things. Kyanite, the above is kyanite and A. Okay, so this uh, chloride reacts with potash feldspar. So potash feldspar is basically not here. So chloride is connected to this biotite. Okay, that means chloride reaction gave the biotite. Okay, this is chloritoid. This is chloritoid. Chloritoid is generated when there is a Fe rich pelite. Okay, when there is a Fe rich pelite. See, chloritoid may first be introduced into some Fe rich pelite by the reaction chloride plus pyrophyllite gives chloritoid. Okay, basically pyrophyllite, PRL is pyrophyllite. So pyrophyllite composition is aluminous in nature. Okay, aluminous in nature. Okay, that's why see here this chloride is joined with aluminum A side and they are joined with chloritoid. This is chloritoid position. Okay, the positions of particular minerals are fixed in a KF or SCF diagrams. Okay, because this is also a QFF like type of diagram. Na you are calculating based on the amount of if you will plot a rock particular if you will plot a particular rock, then it will get on a zone. Okay, if you plot a particular oxide, then it will get only that fixed position. Okay, oxide will get particularly fixed position. So the aluminous zone is the on the above, the chloritoid zone is here. This is a zone, and about this multiple diagrams, multiple lines connecting. So this multiple lines basically represent a solid solution. Okay, basically represents a solid solution. Now here I was showing you like this this xy gave xz. So x plus y gives x plus z or y gives z. Okay, if I am plotting these lines like this. Okay, now this represents a solid solution. That means if x is constant, it is starting from a same point. So x and z, this composition x and z, this reaction can occur in a wide variety of uh, molar proportions. Okay, wide variety of molar proportions. Like I will say olivine is formed if it is olivine, and if it is like your silica, considering only. Okay, only considering, not this is not a realistic one, so hypothetical one only. Olivine and your SiO2. So then this will be your olivine and SiO2, and then this will be your enstatite. Now this olivine and SiO2 enstatite is not valid for only one composition. This is available for wide range of composition. Like this olivine can be phosphorite, this olivine can be phyllite or the hyalosiderite. Okay, so these things can be here. So for FO phosphorite there is a line, for phyllite there is a line, for hyalosiderite there is a line. Okay, these represent solid solution, means a wide range of composition can be possible. Okay. So this chloride reacts with pyrophyllite and forms the chloritoid. Okay, forms the chloritoid. Apart from that, chloride can also react with moscovite and can give annite. Okay, can give annite. What is annite? It is a biotite. Okay, annite is a biotite. Basically, in this reaction, epichloride breaks down by this reaction to form Fe-biotite. Okay, Fe-biotite is annite. Annite is a Fe-rich biotite. So this in the biotite zone, what happens? The chloride in the previous zone that reacts with potash feldspar and gives biotite plus muscovite. And if the pelite is Fe-rich, then chloritoid will appear, and this chloritoid plays a significant role in this Varovian sequence. Okay. So next, after generation of chloritoid, the Garnet zone. Okay, the Garnet zone. What happens in the Garnet zone? The chloride. Okay, the chloride it reacts with quartz only and breaks down. Okay, to form garnet. Okay, almandine. This is almandine. The reaction for breakdown of Fe chloride to Fe garnet. Okay, chloride breaks down to garnet. So here direct chloride, this quartz cannot be plotted in SCF diagram, so quartz was plotted in outside, just represented outside. Okay, so this Fe chloride directly breaks down to almandine. That's why this chloride is directly joined to this garnet thing. Okay, this line chloride is directly joined to the garnet thing, but these things are previously available now. The reactions we have plotted previously, so these are previously on, or they are only the change is occurred here. You can see here from this diagram to this diagram, the change is this field only. Okay, from this diagram to this diagram. Okay, the change is only this field. You're getting it? Everyone getting it now? This is the place. This was there, this is also there. This place garnet appears. This is there, this is here, only garnet appears. Okay, so chloride directly breaks down to garnet. Like this only the diagrams are studied. Okay, clear? Chloride directly breaks down when temperature pressure increases. Okay, I forgot to mention the temperature here. If chloride is less anomiyous, it may break down to almandine plus a small amount of Fe-biotite. Okay, if chloride is less aluminous, it will break down to almandine plus anite, Fe-rich biotite. Okay, so these things are simply just written. Okay, you can go through these things. Nothing to make you more you will get it more in a more understanding manner. Nothing there. Only the reactions. Okay, these reaction you will remember on reaction, that is enough. These reactions cannot you can need not to be remembered. Okay, it is very impossible thing to uh, memorize these things. We are not chemistry students, we are geology students. Okay, so if you chloride breaks down to almandine presence of in the garnet zone. Next comes your sterolite zone. Okay, where the sterolite zone? Yes. So here sterolite zone. So here see this thing chloritoid. This chloritoid. This chloritoid reacts with kyanite, gives sterolite. Okay, chloritoid reacts with kyanite. This chloritoid appeared in which? Appeared in biotite zone. Chloritoid appeared in biotite zone. Now, biotite zone when or why? because if there is Fe rich pelite, then only chloritoid will appear. If there is Fe rich pelite, then only chloritoid will appear. We have studied earlier in the earlier slides. So now if there is no Fe rich pelite, then this storolite zone will be not there. You are getting it now? If there is Fe rich pelite, then in the biotite zone, chloritoid will appear. Okay, chloritoid will appear. If there is no Fe in the pelite, then chloritoid will appear or not? Simply chloritoid will not appear. Okay, chloritoid will not appear. So if chloritoid will not appear, then there will be nothing to react with kyanite in the storolite zone. If there is nothing, then technically the storolite will not appear, na, because there is no raw material for this storolite production. Okay, storolite production, there is no raw material, that chloritoid is not available. Okay, apart from that, chlorite, chlorite plus pyrophyllite, okay, gives chloritoid. This pyrophyllite is aluminous in nature. The reaction. So if there is not aluminous thing, okay, not aluminous rich, then the chloride zone will also not appear. Okay, then also the chloride zone will not appear because chloritoid requires two things. One is Fe, one is Al. Okay, the pellet should be Fe rich, the pellet should be aluminum rich. If these two conditions do not satisfy, then sterolite zone will not appear, and technically this sterolite zone, this like the reactions or the metamorphism or the area under metamorphism is under Garnet zone only. Okay, is under Garnet zone. Everyone getting it? To the next, here it is represented by the diagram. This chloride, okay, sorry, chloritoid. This chloritoid is joined with sterolite with the help of kyanite. Okay, kyanite, chloritoid gives sterolite. Okay, here we can okay, garnet, chloride, sterolite. What this, where this diagram came from? Chloritoid continue to break down. Okay, here in the sterolite zone, what happens? The chloritoid reacts with kyanite, gives sterolite. Okay, sterolite plus chloride. After that, this chloritoid continuously breaks down. Okay, chloritoid continuously breaks down to garnet, sterolite. Chloritoid continue to garnet, chloride, sterolite. Okay, continuously breaks down with increasing temperature, and the chloritoid exhausts. Okay, one of the phase exhaust. That's why in the second diagram we are not getting in chloritoid. Okay, we are not getting in any chloritoid. The chloritoid zone is completely replaced by sterolite because all of the chloritoid are converted to sterolite. Okay, ठीक है? Okay. So in the next, it is kyanite zone. Kyanite is formed at 630 degrees Celsius in the Barrovian sequence. 630 degrees centigrade. Here what happens, this sterolite in the previous, it reacts with chloride and forms the kyanite plus biotite. Now we will say, if sterolite is not there, how will the kyanite isograde will appear? If there is no sterolite, then chlorite will directly convert to kyanite in presence of muscovite and quartz. Okay. Above the kyanite isograde, the chloride kyanite biotite triangle continues to migrate towards higher MgFe caused by a continuous reaction. Okay, chloride will directly convert to the kyanite plus biotite, but it will require a higher temperature. Okay, it will require a higher temperature than the normal 630 degrees Celsius. If sterolite is there, then in 630 degree temperature the kyanite zone will appear. If sterolite is not there, then some higher temperature will require. Okay. The sterolite out isograde. Sterolite out isograde means sterolite is getting out from the or getting exhausted from the system. Sterolite converts to garnet plus biotite plus ALS. What is this ALS? I have to see ALS. Okay. Aluminosilicates maybe. So sterolite out. This is sterolite out isograde. In isograde and out isograde. This is the thing you have to understand. What is in isograde and out isograde? If you write CpG SKS, okay. So this will be your biotite in isograde, and this will be biotite out isograde. Okay. Here biotite will appear, and here garnet will appear. This biotite will be converted to garnet. So this is biotite out. This is biotite in. This biotite out is also garnet in. Garnet in. This garnet out is also sterolite in. Getting it? Okay. So next is your the sillimanite zone. After kyanite zone, the sillimanite zone is a simply polymorphic transformation. Okay, sillimanite zone after kyanite formation, na here kyanite form, here kyanite form. After kyanite formation is just very high. Sillimanite is a very high temperature variety of kyanite. So the kyanite directly polymorphic transform. Kyanite is transformed to sillimanite. Okay, with high temperature. There is no reaction here. Only the kyanite transformed to the sillimanite. Okay, this was the medium temperature pressure classical Barovian sequence. Everyone got it, or anyone having any doubt? Basically, PTT path. PTT path. Okay, that means pressure, temperature, time. Okay, pressure, temperature, time. Metamorphism is a process, okay, which is highly dependent on these three things. Highly dependent. Pressure, temperature, and time. It requires a long amount of geological time, temperature and pressure changes. So these three entities, taking these three entities, we have like created a diagram. We have created a diagram, okay, or you can say a line, or you can say a path, curve path, which represents the conditions, the PT conditions, particularly the PT conditions, okay, PT condition faced by that area, by the area under observation, or area under metamorphism, you can say, area under metamorphism. Okay, so this PTT path represent these things. This is a PTT path. This is pressure, this is temperature. Okay, PT. And time is like how this PT is changing. Okay, how this PT is changing. Okay, it is like a PTT path is like a PTT. So it is, this is small t, and time is small t. This is like a set of pressure and temperature conditions. Okay, set of. Okay, this PTT path is a set of pressure and temperature conditions plotted on PT graph. Okay, plotted on PT graph. So basically, this PTT path, you can see here, this is prograde, this is retrograde. Grade basically represents the temperature, you know. Grade basically represents the temperature. So prograde means increasing temperature, or retrograde means decreasing temperature. This is temperature line, na? This is temperature line, x-axis. So temperature is decreasing, temperature is increasing. Okay, prograde, retrograde. Okay, this is, you can say, constant temperature. Okay, this is the peak of metamorphism. Why this is peak of metamorphism? Because here pressure is also high, temperature is also high. But this is not the peak, because temperature is not highest, only the pressure is the highest. Okay, only the pressure is the highest. Peak of metamorphism will be the point at which pressure and temperature both are high. Okay, both are high. That will only the peak of metamorphism. Okay. So everyone understood what does a PTT path represents? This one, high grade. Grade basically represents the temperature, na? This is the high pressure. This is high pressure, na? This is not high temperature. Okay. So yes, high pressure is here. High pressure metamorphism is here. But this is the peak of metamorphism. Okay. So this is PTT path. Everyone getting an idea that how what a PTT path represents. Yes. So now we'll go paths. We'll go paths. There are two type of paths. Okay. One is clockwise path. One is anti-clockwise path. Okay. There are two type of paths in PTT path. PTT paths are of two types. You can say one is clockwise. One is anti-clockwise. Now you can see here, if I am plotting two diagrams, this is clockwise, okay, and this is anti-clockwise. Okay, so if you have understood what I've told, kindly tell me, kindly tell me regarding pressure and temperature. This is diagram 1, this is diagram 2. How the change is occurring, okay, how the change is occurring, like in the diagram 1, pressure is increasing or temperature is increasing fast, then temperature is decreasing or pressure is decreasing second, subsequent following. Like in the second diagram, the temperature is first increasing or pressure is first increasing. Okay, right and same. See, okay, see, so here, hello, so here see, if you will tell pressure and temperature both are increasing, then both should increase like this. Okay, and decrease like this. Okay, this is pressure, this is temperature. Okay, if there is a diagram, if you will call only pressure is increasing, then the diagram should be like this. Only pressure is increasing. Okay, and pressure is decreasing. But here there is also change in temperature. Na? This is the temperature 1, this is temperature 2. Temperature also increased. But this increase in temperature, this difference is not as much high as this difference of pressure. Okay. That's why we only tell that pressure is increasing. Okay. That's why you only tell that pressure is increasing. Okay. Like that, if we are considering this thing, if we are considering this thing, okay, sorry, like this thing, okay, So here temperature is increasing rapidly. Okay, because the first temperature was here, here, then it was here, then it is here. This is the temperature values. Okay, these are the temperature values. Okay, one, two, three, four. But if we will compare this with the pressure variation, then this pressure variation is much more less than the temperature variation. Temperature variation is 4, but pressure variation is like, it will be like 1, 2, 3. That's why we consider it this as a temperature increase in temperature. Okay, increase in temperature. This actually this depends on the on your view only. That if you are considering this curve will represent increase in pressure. Okay, but this curve will represent increase in temperature. You are getting it. Here pressure also increasing, temperature also increasing. Here also pressure increasing, temperature also increasing. Here the first pressure, but the difference is very less, na? So we tell that yes, temperature is increasing. Yes, here pressure is increasing. But hello. So uh, okay, we'll go to this subduction zone. Okay, subduction zone and mid-oceanic ridge. Okay, we are plotting two diagrams for the both. So in case of mid-oceanic ridge, you know this is temperature, pressure, this is temperature and pressure. First, what will happen? There will be increase in temperature. So increase in temperature. Then what will happen? So basically, pressure will increase because of the formation of new rocks. Okay, because of the formation of the new rocks. So you can see here. So this is rifting. Okay, this is rifting. MOR. Okay, MOR. You can see here. Okay, what happens? First temperature increases. Okay, first temperature increases because of the rifting. The magma comes out, na? The temperature increases. Then what happens? The rocks are formed and the lithostratigraphic pressure increases. Then the rifting closes and the temperature decreases simultaneously in the long process. Okay, the temperature decreases simultaneously with pressure because of the formation of the new rocks. Okay, so this will be a path. Temperature increases, then pressure increases, then temperature decreases. Okay, as rocks are there, lithostratigraphic pressure does not decreases to a significant extent. Okay, only a small amount of decreases there. This will be a anti-clockwise path. So for MOR, there will be an anti-clockwise path. Everyone got this? How for MOR there is an anti-clockwise path? Now, if we'll go to the collision area, in the collision area, the pressure will increase if increase first. So this diagram will like this. Okay, the pressure will increase. The pressure will increase first. The pressure will increase first because there is subduction. Okay, subduction creates high amount of pressure. This is a high pressure, low temperature area. MORB is mid-oceanic ridge is a high temperature, low pressure. This is high pressure, low temperature area. So pressure will increase first. Subduction process will occur. Then pressure will decrease after the But after the break, after the like you can say the locking, here the plate is locked, and if the what it is called accretional prism it fails, the pressure decreases. Okay, so pressure decreases, but not to a significant extent. Okay, not to a significant extent. Apart from that, temperature also increases. How? The melting process occurs, and due to the lithostratigraphic pressure and due to the bottom part of the earth, the temperature also increases. Okay, and after mantle melt, sorry, after the partial melting of the plates, temperature increases, and then the volcanism occurs. Okay, the arc forms, volcanic arc, island arc forms, and after the process, that what happens now, the volcanism is active in Japan area. Okay, Hawaii area. Hawaii is a hotspot. Japan area, you can say Japan, or you can say the Sunda Trench. Okay, Sunda Trench, the Barren Island volcano. Okay, Barren Island volcano. This is active now because melting is occurring there. So one time it will call that it will come that melting will stop. Okay, subduction process will be completed. At that time, what will happen? The temperature will decrease. Okay, the temperature will decrease. Pressure decreased, then temperature will decrease. This is the clockwise path. Clockwise path for collision or subduction, you can say. Okay, everyone got it? That how a clockwise path will take place, how a anti-clockwise path will take place. ठीक है? So these are prograde, retrograde, common types of PTT path. Prograde, common types of PTT path, clockwise, anti-clockwise, dependent upon horizontal and vertical axis. Okay, and how difference maximum pressure and maximum temperature. This is not of the like thing, important thing. How PTT paths are determined. Okay, PTT path, how, क्योंकि हम लोग जो देखते हैं वो रिजल्ट देखते हैं, we see only the results. So we have to like how we will imagine that this pressure, the pressure was in this condition, the temperature was this condition. Again we go back to this thermometer and geobarometer. Okay, geothermometer and geobarometer concept. Okay, so using this geothermometer and geobarometer, we get the pressure and temperature conditions. Okay, the change in texture, structure, mineralogical change, hence recorded, reconstructed an approximate PTT path that it might have undergone. The change in texture, structure, and mineralogical change. This only represents the PTT path. Okay, these are the geothermometers and the texture. From the texture, we can identify the mineralogical change. Which mineral replaced which mineral, what at what temperature at or at what pressure this reaction occurs. Okay, the garnet growth zoning, the garnet growth zoning occurs at which zone occurs at which place, which pressure temperature condition. From this condition, we get the pressure, temperature, and okay. Now you can see the Andalusite. Okay, sorry, right inclusion field. Okay, these are the key inclusions. Okay, these are the key inclusions. What happened? See here what happened? Garnet. is replaced by kyanite. These are kyanides. Okay, these are kyanides. So this reaction occurs at a particular temperature pressure condition. Okay, so when we will get this type of rock in a particular area, this type of texture, okay, we can identify or we can say that the pressure temperature condition at the formation of this rock was like this thing. Okay, so like in case of methods of inferring, I have told you about zoning. The zoning. Okay. Garnet geological response of a mineral to the changes may be recorded in minerals that have crystal chemical structure characteristics that allow composition acquiring early in the mineral growth history to be preserved during the later stage of the growth at different conditions. Okay, जब different conditions आएगा तो वो growth zone के हिसाब से these are the this is garnet growth zoning, and you can see these zonings. This is like yellowish color, and from the outward the zone it is getting dark violet color. So these zones actually represent different compositions, and these compositions will represent different pressure and temperature condition. This is a single mineral garnet, but they have your changed the composition due to the temperature and pressure condition. Okay, you can see also here these are zones. Okay, from these things only we can determine pressure and temperature condition. Okay, pressure and temperature condition. Apart from that, there is symplectite texture, corona formation. Okay, corona you have already studied in igneous texture, corona formation, symplectite texture you know. Okay, these are the things where from where we infer the pressure and temperature, and from there only we calculate the pressure and temperature path. So basically in temperature and PTT path, you first give your introduction that PTT path shows this thing. After that, you tell that this PTT path can be clockwise and anti-clockwise depending upon the PT history followed. After that, you can show that this prograde path and retrograde path. This is prograde and this is retrograde. Okay, prograde is increasing temperature pressure, retrograde is decreasing pressure temperature. Then you will show anti-clockwise and clockwise path and give your example with anti-clockwise will be the rifting case and clockwise will be the subduction case with the proper description. Okay, everyone got the PTT path?